Probably the simplest way to describe a solution is to use the weight in weight formula. Weight in weight means that we describe as a percentage the weight of solute relative to the final weight of the solution. I'll give you an example. As a formula, I could say take 3 grams of dye and mix it with 97 grams of alcohol to give a final solution that we call 3%. A short way of saying that is to make a 3% solution weight in weight. And what that simply means is we take 3 grams of dye, we take 97 grams of alcohol, we mix them together. Very simple. We don't have to do it volumetrically. We measure our volume of liquid once, mix it up, and we're all taken care of. One point I do need to mention, though, when we deal with weight in weight, is that the final weight that you wind up with for the solution, the quantity that is not the same as the final volume. If you have 100 grams of solution, that doesn't mean you have 100 milliliters. Now, I'll give you another practical use for a weight in weight solution, and that's with microbiology. We work with, I'm going to demonstrate here actually. Let me show you some tryptic soy agar. This is a typical medium that we use in microbiology. Agar is a seaweed extract that when it's heated up in order to pour plates gets awfully gooey. Contains proteins as well which stick to surfaces. If I try to prepare a solution of tryptic soy agar volumetrically, I'm going to dirty up a cylinder, I'm going to dirty up a flask, I'm going to have to pour it in a bottle for sterilization, all the while coating all those surfaces with agar and protein, leaving a lot of it behind. It is very convenient to describe these kinds of mixtures in weight as weight in weight. The instructions here say simply to take 40 grams of tryptic soy agar powder, mix it with 1 liter of water, and then go ahead and heat it until it's dissolved and take care of it, sterilize it, and we're all set to go. What we do then is we measure out a weight of pure water into the container we're going to use. Water, pure water, weighs 1 gram for every milliliter. So with water, thank goodness, we don't even have to measure a weight. We can simply measure a volume. It's one of the convenient things about aqueous solutions. We can simply put the amount we want. Let's say for this bottle, I want to leave room for pressure changes when we put it in the sterilizer. So I'm going to make 500 milliliters of this stuff. I'll put 500 milliliters of deionized water in the bottle. I will add 20 grams of tryptic soy agar, mix it up very carefully, and I'm done. I don't dirty a cylinder. I don't mess with beakers. This is what it would look like, by the way, if I take tryptic soy agar and I mix it with water. It is a goo. It sticks there. It sticks to everything. It sticks to the side of the vessel. We just don't want to mess with that. We want to mix it in one container and be done. So weight in weight, in the case of microbiological medium, that's about full, is a very convenient mechanism to use. And it beats the heck out of weight in volume, which is the next one I'm going to describe. There is one caveat to describing solutions as a percent weight in weight. Whenever we describe a percent solution, most of us assume you mean weight in volume, which I'm going to talk about next. If you really want to mean weight in weight, then when you describe your percent, let's say 3% dye in ethanol weight to weight, you need to say weight to weight, so you distinguish it from weight in volume. When I read a formula that describes a solution as a percent, I automatically assume they mean weight in volume. And if you write a formula as a percent, I think the people who read your formula are going to assume the same thing. The reason is that weight in volume is more commonly used than weight in weight, mainly because most of our solutions in biological sciences are aqueous. 1 gram of water is the same as 1 milliliter of pure water under standard conditions. When we measure something or describe a formula, weight in volume, we're describing the percentage of a solute as a percentage of as a proportion of the final volume of the solution. For example, a 1% solution of sodium chloride, I'll just go back to that old standby, is 1 gram of sodium chloride per 100 milliliters of solution. It is percent in grams of volume in milliliters. If I read a formula that is written as percentage, I assume that the percentage means percent weight in volume, not weight in weight. And the reason is that weight in volume is a more common way of representing formulas. Now, we use weight in volume typically when we're preparing very simple salt solutions, and we really don't care about the molarity, how many moles of reactants we happen to have per unit volume. We also use weight in volume instead of moles per liter because or when we're working with a substance that's, say, naturally acquired, something that's acquired from as a natural product, such as a plant extract, maybe a digestive meat or soybean that we use for microbiology, or a complex dye for which we have no known molecular formula. In fact, many of our complex mixtures can't be described as a single molecular formula because they consist of multiple different types of substances. So in that case, we can't use moles per liter. We can't use molarity. We use weight in volume or even weight in weight. In weight in volume, we measure a particular amount of the substance that will be a percentage of the final volume of the solution. A 1% weight in volume solution is 1 gram of solute per 100 milliliters of the solution. 10 grams per liter, 1/10 of a gram per 10 milliliters. That's the proportion. It's a little hard for some people to remember that formula. So I use the rule of thumb that if we just keep in mind that 1 milliliter of water weighs 1 gram, then a 1% solution is 1% of the volume of pure water by weight that makes up the final volume of the solution. So 1% is 1 gram per 100 milliliters. 100 milliliters is 100 grams of pure water, and 1 gram is 1% of 100 grams. It's a little trick, a little means of trying to remember the formula. Now, what I'm going to do as a demonstration is to measure out a quantity of 0.85% sodium chloride. That is 0.85%. I always put the 0 there ahead of the decimal when I write things down because it's very easy to overlook a decimal point. 0.85% sodium chloride solution is compatible with cells and tissues of vertebrates. Sodium is the principal electrolyte outside of cells, the positive cation that is. Sodium chloride being the cation plus anion combination. Whereas inside cells, the organelles and other cell structures are much more, the insides of membranes, for example, are much more compatible in a high potassium environment. So if I'm going to isolate an organ, let's say remove a liver and put it in a saline solution, or prepare some cells from tissues and suspend them very quickly before moving them someplace else, I'll start off by rinsing everything off with 0.85% sodium chloride. When we use physiological saline, we typically use a lot of it, especially for a large teaching lab. So I'm going to make 2 liters of this stuff. Now, at 0.85% sodium chloride is 0.85 grams per 100 milliliters. So for 2 liters, or 2,000 milliliters, I'm going to need 20 times that amount. That is 2 times 8.5 grams, which comes out to 17. So I'm going to go ahead and weigh out 17 grams of sodium chloride to make my 0.85% weight to volume solution. I'm going to the balance here. I'm going to place my weigh paper on there. Again, I need to tare the electronic balance so it's reading 0 grams. Now I'm going to take my sodium chloride. I've already cleaned off the pipette, inspect, it looks pretty good. I don't want to dip a dirty pipette into my container. And I'm going to go ahead and carefully, let's see what we got there. Okay, I can dump all that in there. I'm going to carefully weigh out 17 grams. Sometimes I can hit this right on the nose with one spatula full. Sometimes it takes a little longer. 16.8 is just about there. Okay, whoops. Let's take a little bit extra off of there. There we go. Wow. 17.00 right on the nose. Look at that. That's just ridiculous. I didn't want to do that. I wanted to add a little more. The reason I wanted to add a little more is just to point out that it doesn't have to be 17.00 right on the nose. If I wanted a very, very accurate physiological saline solution, I would have said 0.8500%. 17.1 grams is just fine. Oh, 17.00, I'm very proud of that, but 17.1 is close enough to 17. Anything between 16.5 and 17.5 is good enough to make a 0.85% weight to volume solution. If I wanted, I could go with 17.0 and then something like 17.05 or 16.95, somewhere in that range would be fine. But we don't need to be accurate to as many places that are on the balance, and don't ever try to do that. Now I'll simply take my 17 grams of sodium chloride solution, and I'll take my flask, in this case a 2-liter flask over here. I'll add some water to about the 1800 milliliter mark, swirl it up, dump my material in here, and after it's fully dissolved, I will use a graduated cylinder to produce the final volume, make sure it's thoroughly mixed, and I'll distribute it into bottles for the class. If we're only working with liquids, then volume in volume is a very convenient way of describing a formula. For example, in histology, we work with various grades of alcohol, concentrations of alcohol, in order to dehydrate our samples. To make 70% alcohol volume to volume, we would simply take 70 milliliters of 100% alcohol, pure ethanol, usually denatured, and we would mix it in a final volume of 100 milliliters with distilled water or deionized water. The alcohol then is 70% by volume of the final volume of the solution. We can get pretty close by simply mixing 70 milliliters of ethanol or alcohol with 30 milliliters of water, but because they are somewhat mutually soluble, the volume might be a little less than we think. So we refer to volume in volume, meaning volume of solute, in this case ethanol, as a percentage of final volume of the solution that we're preparing. Now, as a demonstration, I'm going to prepare what we call a destaining solution. In electrophoresis of proteins, we run our proteins through an electric field on what we call a gel. The gel starts off clear. After we finish our electrophoresis, we have the proteins distributed to form bands in the gel. To see the proteins, I use Kumasi blue dye, 1%. I'm not going to talk about making the stain. I'm going to talk about how we get rid of the stain. The dye stains the entire gel uniformly. It binds rather permanently to the proteins and is simply there in solution inside the gel. So in order to visualize the protein bands and wind up with some very nice gel patterns, we use what we call a destaining solution. And the first of 2 destaining solutions that I use consists of 50% methanol, 10% acetic acid. Acidic alcohol keeps the proteins precipitated. And then it's an aqueous solution. I don't even mention the water. But it is 50% water. What I'm going to do now is get my water and get my cylinder, and then we'll step over to the sink, and then we'll step over to the hood and go ahead and add the acid and the alcohol. All right, here we are at the fume hood where I keep my acids, I keep alcohol, and so on. Notice I'm wearing a lab coat. The materials I'm using here don't present a terrible hazard, but it's important to take precautions. I'm also going to wear my eyeglasses, which will work. They'll be satisfactory as safety glasses for this. Glacial acetic acid is corrosive, and it can cause burns, of course, as with any concentrated acid. Methanol is poisonous, but otherwise it doesn't represent a terrible hazard. Well, it's also flammable, so we keep it away from flames. As we should remember from chemistry class, the rule of thumb is to add acid to water rather than vice versa. The reason we do that is when we mix acids and waters, we generate heat. If we add a large quantity of water to a very small quantity of acid, the volume is initially low, and the heat generated can be such that it can crack the vessel. An excess of water acts as a heat sink, so if we add acid to water, the heat is generally dissipated throughout the volume, and we don't have as high a risk of cracking a vessel and causing an accident. Well, I'm going to step over to the sink here and partially fill my 2-liter cylinder. I'm using a 2-liter cylinder for all my measurements because we don't need extreme precision for a destaining solution. The purpose of the darn thing, after all, is just to rinse out an excess of dye. That's 830. Let's pour a little bit out there. It's about 800. It's close enough. Again, we don't need to be that precise. Now notice how clean my deionized tap is. Boy, that's nice. I don't have to clean it because the water's so doggone clean. It just stays this way. Notice on my hot and cold water tap, you may be able to see this, there is a lot of deposited material around the outlet. That's because this stuff carries solutes, it carries all sorts of chemicals in it. A lot of calcium and so on that becomes deposited on the surface, and that would go into our solutions if we use tap water. Deionized I use for most of my applications unless I need a very analytical, very precisely controlled solution. I'm going to step back to the hood and finish making my destaining solution. I said we needed 50% methanol. That would be 1 liter of a 2-liter solution. And so I'm going to go ahead and make up this stuff. I have 800 milliliters in there, roughly, so I'm going to fill this up now to 1,800. Now, I hope I have enough. That's good. When we read the volumes in a cylinder, we are advised to read the bottom of the meniscus. That gets us close, but consider that surface tension, here comes good old surface tension again, causes us not to have a terribly flat surface, especially when we work with small graduated cylinders. So reading the bottom of meniscus is no guarantee that we have a precise volume. This is accurate enough. We're right there. This will be 50% methanol when I finish with the acid. It's a little warm already, my goodness. Glacial acetic acid is concentrated acetic acid. It really is more like 37%, I believe. But when we talk about 10% acetic acid, we talk about, again, 10% by volume of glacial acetic. I'm going to go ahead and add this to my 1,800 milliliters. There will be some heat, but it doesn't matter because the volume of this liquid will absorb the heat. There's my final solution. This will mix on its own, but what I'll do is pour this into a brown bottle, one of these large 4-liter bottles that's been rinsed out. I will label it, of course, so I know exactly what it is, and then I'll swirl it up to mix. My destaining solution is ready. It's not terribly flammable, being only 50% methanol, but I'm going to store it in a flammables cabinet anyway, just to be on the safe side. So far, we've talked about preparing solutions as a percentage. Weight in weight, weight in volume, volume in volume. There's a disadvantage to using that method. The weight of substance per unit volume, for example, tells us nothing about the number of moles of material, the number of molecules per unit volume. Suppose we want to produce a chemical reaction between substance A and substance B. The molecules of substance B are heavier than the molecules of substance A. If we take equal weights of both, mix them into a solvent, we have less of B than we do of A because B is heavier to start with. But if we take equal numbers of moles of A and B and mix them, we have precisely equal numbers of reactants. There's another disadvantage to using a percent to describe a formula, and an advantage to using moles, and that is that chemicals come in different forms. For example, I have calcium chloride here on my bench. This one is, the one in my right hand, is calcium chloride anhydrous. Anhydrous means that it is just calcium chloride. There might be a little water in here because it's humid in the lab, but it started off as pure calcium chloride. Over here I have calcium chloride dihydrate. This is a hydrated compound. For every calcium chloride molecule, there's 2 molecules of water that were originally hydrogen bonded to the calcium chloride. The molecular weight or formula weight in grams per mole of calcium chloride dihydrate is higher than the molecular weight of calcium chloride when there's no water. If I mix the same amount in grams of this form of calcium chloride as this form, I get two different concentrations in moles per liter, two different concentrations of reactants or molecules. On the other hand, if I determine how many moles are in a particular amount or weight for this substance or this substance, and I prepare my solution as a molar solution, it doesn't matter which one I use. The hydrated compound with its two extra water molecules becomes calcium chloride, just like this one does. The water molecules become part of the solvent. And when I bring up the material to the final volume and I make my solution, this water molecules become part of the solvent molecules. When I prepare a solution by molarity, I need three pieces of information. I need to decide what volume I'm going to prepare, and I try to convert that volume to some standard unit, usually liters. I need to know the concentration to which I'm going to make the solution. I generally express my concentration in moles per liter, or molarity, capital M. I also need to know the relationship between number of moles and number of grams of the substance I'm using for the solute. That is the formula weight, also known as the molecular weight. We call it a formula weight because there may be inert ingredients in there. Sometimes it'll be referred to as molecular weight. And it's usually printed on the bottle here. I'll talk about a little more about that in a moment. In order to decide how much to weigh out in order to prepare our solution, we take the volume in liters, preferably, multiply the volume which is desired by the desired concentration in moles per liter. Moles per liter times liters. The liters cancel out. You've got just moles desired. Take the number of moles desired times the formula weight in grams per mole, and it gives you grams to weigh. Once again, convert your units to something that's standard, so all your volume units are the same, all your moles are the same, all the units of mass are the same. Multiply desired volume times desired concentration times grams per mole, the molecular weight, and you've got the amount to weigh out for a given solution by molarity. Let me talk a little bit more about formula weights, because you're going to be reading weights off of chemical bottles, and you're going to need to calculate an amount to weigh out. And the very same chemical can have a different formula weight depending on how it's prepared and how it's purchased. On the other hand, the molecular weight of, for example, calcium chloride is the same no matter how it's provided. The difference between formula weight and molecular weight can come from a couple of different reasons. One reason is that some compounds come hydrated. I mentioned hydration before, that there's a certain amount of water that is hydrogen bonded to the molecules before they're dried down and bottled up. That water remains bound to the molecules in a known proportion. Thus, we might have calcium chloride with no water. We might have calcium chloride dihydrate. Another form is calcium chloride hexahydrate. The molecular weight of calcium chloride is 110.99 grams per mole. All over the world, no matter how it's prepared, that is its molecular weight. But the formula weight for calcium chloride can vary depending on state of hydration. The formula weight, for example, for calcium chloride dihydrate is 147 grams per mole. And, pardon me, I have to read this one. The formula weight for calcium chloride hexahydrate is 219.1 grams per mole. If we take 147 grams of calcium chloride dihydrate and we mix it into a final volume of 1 liter into water, we will have 1 molar calcium chloride, CaCl2. If we take 219.1 grams of calcium chloride hexahydrate and we mix it into water to a final volume of 1 liter, we have exactly 1 molar calcium chloride. Both forms of calcium chloride give us the very same concentration, but we need different amounts, different masses of the material depending on how it's prepared, depending on the formula weight. Same thing with calcium chloride anhydrase. 1 molar is simply 110.99 grams per liter of final volume of the solution. There is another reason that we work with formula weights, by the way, besides hydration, and that is sometimes our compound comes as a salt form. we might have the sodium salt of a particular compound, the potassium salt, and so on. And in part 3, under tricks of the trade, I think I'll talk a little bit about salts and how we work with them. And finally, a lot of compounds come with inert ingredients. So if you have something that is 75% pure, the other 25% being completely inert, you can ignore it. The formula weight will tell you how many grams you need in order to get a particular mole of the active ingredient. Again, we work with the formula weight, and that gives us a final result that can be used to make a molar solution. When we prepare molar solutions, no matter how careful we are, we sometimes run into complications. One complication I've already mentioned. Some of our materials contain inert ingredients, and they aren't 100% pure. If we really have to, we can go ahead and compensate for the lack of purity and increase the amount that we use to make our solution. Generally, though, you'll see something that says such and such a compound is greater than 99% purity. Fine, treat it as 100%, don't worry about it. 1% of something in biology is usually meaningless. Another complication is that sometimes we don't know the formula weight. The label fell off, or it's been obscured by somebody, or they put it into another bottle and forgot to label it. We hope you don't use it at all, but sometimes we get desperate. If you don't know the formula weight, it's not printed on the bottle, you might be able to find it in a catalog from a chemical company, or if you have to, you can calculate a molecular weight, if you know the stuff is fairly pure, by looking at the molecular formula, looking at the atoms, and then going to a periodic table and getting the actual atomic weights. Add them all up and you've got the molecular weight in grams per mole. Finally, we run into a problem, especially where I work in Houston, Texas. It gets so humid here that a lot of my chemicals, if I'm not very careful in storing them, become hard as a rock. Especially microbiological media, they just become solid because they accumulate water. The water reacts and they wind up solidifying my chemicals. What happens is that some materials are what we call hygroscopic. They tend to collect water. Magnesium chloride is especially notorious for accumulating water. You'll go into a formula or a bottle to pull out magnesium chloride, and it's floating in a slush. This is a problem. And there isn't a really good solution, particularly for something as hygroscopic as magnesium chloride. What I do is I try to use the stuff fresh. If it says there's 500 grams in the bottle, I make up 500 milliliters of a 1 molar solution, or maybe a liter of a half molar solution, and then I use the stuff as a stock solution. That way I'm fairly sure I've got the right concentration. Another thing to do is to put the stuff in a desiccating jar and try to keep it desiccated in a completely anhydrous environment. It's tough to do sometimes, though. As for most chemicals, sodium chloride, microbiological media, as long as they're kept fairly well dry, we don't worry about there being hygroscopic. We know there's moisture content in here. It's not the same as hydration, by the way, but this is simply accumulated moisture from the environment. We just can't be that accurate, and this is another reason why we don't try for extreme accuracy when we try to make up solutions. Why should we weigh out a chemical to 1/10 of a milligram on an analytical balance when we have an unknown quantity of water that's contributing to the weight? It just doesn't make any sense to be overly analytical when we're making solutions that require a concentration range rather than a very, very perfect concentration. I'm going to describe how to prepare a molar solution using 70 millimolar sucrose as an example. 70 millimolar is 0.07 moles per liter. I want to make 200 milliliters. 200 milliliters is 0.2 liters. So first of all, I'm going to take the formula weight of sucrose. The formula weight can be determined from its chemical formula, which is C12H22O11. I can go to a periodic table, look that up, we'll be fine because the sucrose I obtain is quite pure. On the other hand, I can look here at the molecular weight. Molecular weight is 342.3 grams per mole. That beats the heck out of going to a periodic table. I'll go with 342.3. The amount per liter should be 342.3 grams per mole times 0.07 moles per liter. That gives us 23.96 grams per liter. I will keep that level of precision for now, and we decide I need 0.2 of a liter of this stuff, so I'm going to take 0.2 liter times 23.96 grams per liter. That means I'm going to need 4.792 grams of sucrose for my solution. Now, okay, 4.792. We describe this solution as 70 millimolar. I didn't describe it as 70.00 millimolar or 71.72 millimolar. Described as 70 millimolar. It means that this doesn't need to be extremely precise. 4.792 rounds up very nicely to 4.8. So what I'm going to do is weigh out 4.8 grams of sucrose. I'm going to be quite happy. One thing I did do, though, is I kept full precision while doing all the calculations. I took my result at the end, rounded it up. All right, now I'm going to go ahead and weigh out the sucrose, make my solution. Now there's two kinds of formulas that you're not going to encounter very often, but if you do, it's a good idea to know what they mean. One of them is molality. Now I'll be honest with you, I have never prepared a solution using a mol-al formula. Molality simply refers to number of moles per unit mass instead of unit volume. And I'm not going to talk about that anymore. You probably never will run across it. Normality is something you will see, particularly when working with acids and bases. Normality refers to the number of reactants in a compound relative to a final product. And it's usually used when we're talking about bases such as sodium hydroxide, acids such as hydrochloric acid or sulfuric acid. When we talk about normality, we talk about number of equivalents per unit volume. For example, or actually moles of reactants. For example, if we have hydrochloric acid releases one hydrogen ion per molecule of HCl. So if we have 1 molar hydrochloric acid, we have 1 mole of hydrogen ions, a reactant, per liter of hydrochloric acid. We therefore have 1 equivalent of hydrogen ions in every mole per liter, or in 1 molar hydrochloric acid. On the other hand, sulfuric acid, H2SO4, releases 2 hydrogen ions for every molecule of sulfuric acid. If we have 1 molar sulfuric acid, we have 2 equivalents of hydrogen ions. And therefore, a half molar of sulfuric acid gives us 1 normal sulfuric acid when we're talking about the hydrogen ions that it releases for use in a reaction. Those formulas you won't use very often, but you will use normality